Hello students, today we are going to discuss about the principle of operation or working of three-phase induction motor. So, as we know that a three-phase induction motor is a singly excited machine, means the energy to the rotor circuit is provided by means of electromagnetic induction, just like as in the case of transformer. So when a three-phase supply is given to a three-phase stator winding, as we have studied in the previous lecture, that a rotating magnetic field of constant magnitude produced, which rotates, or the axis of the rotating magnetic field changes with respect to time. And the speed of this rotating magnetic field is synchronous speed, which depends on the supply frequency and also on the number of poles of the machine. So let us consider a three-phase induction motor whose stator winding carries the three-phase winding, which is displaced by 120 degree. Let us say this is R dash, this is Y dash, and this is blue dash, red, yellow, blue. So when a three-phase supply is given to the stator winding, a rotating magnetic field is produced. A rotating magnetic field means the stator poles, like let us assume that at t is equal to 0, just at the time of switching, the direction of magnetic field is vertically downward. It means at t is equal to 0, the north pole on the stator developed at this location and south pole is at this location. And further, this north pole is rotating in clockwise direction and south pole is rotating in same clockwise direction. So the direction of magnetic field is changing. So let us say at next instant, let us say north pole at this location, south pole at this location. So the direction of magnetic field will be in this direction. So this rotating magnetic field produces an effect of rotating poles around the rotor. The rotor winding of the stator rotor winding of a three-phase induction motor is short-circuited. So an EMF get induced in the rotor conductor by with the influence of this rotating magnetic field. So as we know that it has just the same effect that we can consider an example that the magnetic field is stationary and conductor is rotating in a constant magnetic field. So as we know that according to Faraday law, an EMF get induced in a conductor whose linking flux is changing with respect to time. So either we have to vary the flux by keeping conductor stationary, or if the magnetic field is constant, then to vary the flux linking, we have to move the conductor. So here rotor conductor is stationary, but magnetic field is rotating. Magnetic poles are rotating. So it has the same effect in both the cases. So there exists a relative motion between the rotor conductor and stator poles. Then there will get an EMF get induced in the rotor conductor. Let us see. So let us see at starting, north pole developed at this location, south pole at this location, then magnetic field will be vertically downward. And if we can assume that the magnetic field is rotating in clockwise direction with synchronous speed, and same the south pole in clockwise direction with constant speed, then each rotor conductor influences by this magnetic field, and an EMF gets induced in each rotor conductor. The direction of induced EMF can be found by using Fleming's right hand rule. Fleming's right hand rule means if we keep the thumb, forefinger, and middle finger of your right hand at 90 degrees to each other, then the thumb will show the direction of movement of conductor, with respect to magnetic field, magnetic poles. Here, the magnetic poles are rotating, but conductor is stationary. So we get the same effect if we assume that the poles are stationary. Let us see, if conductor are stationary and magnetic poles are rotating in clockwise direction, it has the same effect if we assume that the magnetic poles are stationary and the rotor conductor are moving in anti-clockwise direction. Then there will be same effect. The conductor is stationary and magnetic poles are rotating in clockwise direction. And in second case, the magnetic poles are stationary and conductor is rotating in anti-clockwise direction. So now let us say according to Fleming's right hand rule, the thumb will represent the thumb will directed towards the direction of motion of conductor with respect to the stationary magnetic poles, and forefinger directed towards the magnetic field, which is in the case it is downward to the plane. Okay. And third, the unknown quantity, which is EMF induced, it will be represented by the middle finger. So in this case, if we consider the EMF in these two conductor A and conductor B, then first we will discuss about the EMF induced in this conductor A. So according to Fleming's right hand rule, the magnetic field direction is downward, and if the poles are rotating in clockwise direction, it has same effect that magnetic poles are stationary and conductor is moving in anti-clockwise direction. Then if thumb is directed towards leftward, that is the conductor is moving in leftward direction, and magnetic field is downward, it means that the EMF will get induced in outward direction. Forefinger is downward, thumb will be in a leftward direction, and the EMF will be in outward direction. So in this case, EMF in this conductor, A conductor, will get induced in outward direction. That is EMF. And now we will discuss about the EMF induced in conductor B. So here, if the conductor is this conductor B is moving in anti-clockwise direction, means rightward direction, and direction of magnetic field is downward. So according to Fleming's right hand rule, if we put the forefinger, middle finger, like a thumb will be in the rightward direction and magnetic field in the downward direction, then the middle finger will be directed towards inward to the plane. So according to Fleming's right hand rule, the EMF induced in this conductor B will be in inward direction. It is represented by a cross. So now we know that the rotor of a three-phase induction motor is either short-circuited through the slip ring, which happens in the case of bound rotor induction motor. And in the case of a squirrel cage induction motor, the rotor is short-circuited with the help of end rings. So in both the cases, rotor forms a closed electrical path. So due to this EMF induced, a current will be circulated in each rotor conductor. So till now, the generating action is completed. Generating action means a rotating magnetic field induces an EMF in each rotor conductor. Now, the motoring action will take place. So now, so far we have discussed that an EMF get induced in each rotor conductor, That is, in this conductor, conductor A, EMF is in outward to the plane, and in this rotor conductor, EMF is inward to the plane, conductor B. Now, motoring action will take place. According to Faraday's second law, a current carrying conductor in magnetic field experiences a force, and the direction of force can be found by using Fleming's left-hand rule. Fleming's left-hand rule. Here, the known quantities are, for each rotor conductor, the known quantities are the direction of magnetic field and direction of current. Direction of EMF induced and direction of current. So, by using Fleming's left-hand rule, we can determine the unknown quantity, that is acting force, on each rotor conductor. So here, thumb, forefinger, and middle finger of the left hand can help to determine the direction of force. So if we put the middle finger in the direction of current, forefinger in the direction of magnetic field, then thumb will be directed towards the direction of force. So here, the middle finger for this conductor, for a conductor, the middle finger will be directed towards outward to the plane, and forefinger will be downward to the plane. Then the thumb will represent a direction towards right. It means on conductor a force will act in rightward direction. Similarly, we can found the force acting on conductor B. So by using Fleming's left-hand rule, we can determine the force acting on conductor V. The forefinger, that is thumb, forefinger, and middle finger. Middle finger will represent the direction of current. It will be inward to the plane, and forefinger will be downward to the plane, and thumb will represent the direction of force, that is leftward to the plane. Now it is clear that the force on conductor A will try to rotate this rotor in clockwise direction, and similarly the force acting on conductor V will also try to rotate this rotor in clockwise direction. Means both the force acting on both conductor will try to rotate the overall rotor in clockwise direction. Hence, a starting torque act on the rotor, which try to rotate from zero speed. And as soon as the rotor will speed up, the relative speed between the stator poles and rotor conductor will reduce. Let us see. Let us say that the stator poles, north and south poles, are rotating with a synchronous speed, which is ns, that is 120 f upon p. And now, if rotor gets an starting torque, and it will get an initial speed and will accelerate. Let at particular instant the rotor speed is given by nr. And if rotor is speeding up, then the relative speed between stator magnetic field and rotor speed will known as slip speed. Ns minus nr. So this is the also known as the relative speed. So as soon as the rotor will speed up, the relative speed between the rotor conductor and stator poles will decrease, and hence the EMF induced in the rotor conductor will also get reduced. Means if ns minus nr, first of all, if nr is increased, ns minus nr will reduce, and hence EMF induced in each rotor conductor will reduce. Therefore, current in each rotor conductor will reduce. and therefore torque developed, force or torque developed on each rotor conductor will reduce. So as soon as the motor will accelerate and achieving some maximum speed, then the value of torque will constantly reduced. And if we discuss about the steady state, if we discuss about synchronous speed, if ns is equal to nr, then slip speed, relative speed will be zero. The relative speed will be zero, then the EMF induced in each rotor conductor will be zero, current will be zero, and finally torque will be zero. So the rotor will fall back. For means speed of the rotor will get reduced by few amount, and if the rotor will get some again some relative speed and a small amount of torque again developed, it will try to achieve again and again synchronous speed, but three-phase induction motor will not run constantly consistently on synchronous speed. So this is the overall principle of operation of three-phase induction motor. Thank you.